Welcome to my presentation. My name is Sungwook Lee and my advisor is Professor Byung. I will be introducing our paper with title EPrOD, Evolved Probabilistic Object Detector with Diverse Samples. In this presentation, I briefly explain the background of probabilistic object detector, we call it EPrOD, and state problems of EPrOD. Then I describe the proposed method to solve these problems. Next, talk about experimental result, and finally conclude this presentation. This slide describes the main feature of the EPrOD. Existing object detector only consider the result of the one class with the highest probability. But this leads to the possibility of pulse recognition. However, EPrOD takes into the score for classes, including the spatial and level uncertainty of the target. At the bottom right, we can see the EPrOD outputs the result considering not only the scores of all classes, but also spatial uncertainty. The figure below shows the overall structure of the Monte Carlo-based EPrOD. We called it MC-EPrOD. This MC-EPrOD adds dropout to some feature maps. Then it accumulates samples obtained through multiple inferences. Finally, the accumulated samples are refined to the final result through a single non-maximum suppression, that is NMS. The statistics are calculated. However, we still found some problems with MC-EPrOD. The first problem is that the detector uses only one image to perform multiple inferences. In this case, there is a concern that identification of object is limited. The second problem is the dropout proposed by MC-EPrOD does not effectively remove the feature map information. This hinders acquiring diverse samples. The third problem is that many boxes accumulated by multiple inferences are refined using a single NMS. In this case, there is a risk of considering even unreliable candidates as a final result. So we proposed evolved EPrOD, we called it EPrOD, to solve the aforementioned problems. EPrOD consists of 4 fundamental techniques. Step 1 uses AlbedoNet to use albedo images together with original images. And let EPrOD perform multi-domain detection. In step 2, diverse samples are obtained by effectively removing the information of the feature map through soft-DropBlock. In step 3, two-step NMS is applied, which is stable for refining the result obtained through multiple inferences. Finally, in step 4, interframe processing is operated to erase false positives that have increased due to multi-domain detection. In the next slide, I will describe each technique in detail. In the albedo extraction step, albedo images are extracted through AlbedoNet. Albedo refers to the image from which shading information is removed. This is used as the input of EPrOD with original images. As a result, it has the effect of additionally detecting objects that could not be detected due to the influence of shading. However, since the conventional algorithm for extracting albedo images has a considerable amount of computation, we propose a CNN-based AlbedoNet. AlbedoNet has a unit structure and is a network that runs image translation from original images to albedo images. This is more than 400 times faster than conventional algorithm. The second technique is a soft-DropBlock that replaces dropout. Feature maps with high correlation between adjacent pixels are only slightly affected by dropout. This can hinder the diversity of samples obtained by dropout. So we analyze the DropBlock method, which can provide diverse samples by removing the local information of the feature map. However, we can observe that the discontinuous boundary of the DropBlock inflicts serious damage to the information required for detection. So we propose a soft DropBlock that smoothly changes these boundaries by applying box filtering to the DropBlock. This also allows you to obtain diverse samples. The bottom images is a visualization of the area where each drop mask is dropping a layer. The third one is stacked NMS. We refine the result through two-step post-processing. The two-step post-processing is advantageous in finally obtaining reliable boxes because refinement is carried out after reducing unclear and overlapping boxes. Then based on the grouping result, the frequency of detected box is calculated, which imposes additional constraint to infer reliable result. Stacked NMS further removes uncertainty on the estimated result by refining the boxes detected for each samples twice. As a result, the boxes can be refined more precisely. The example value can be qualitatively compare the result of each NMS. Finally, let me introduce interplane processing. Because false positives tends to increase when detection is performed in multi-domain, so we use interplane processing to remove incidental false positives. Most of the false positives has no relation to the adjacent planes. We effectively eliminate false positives by erasing undetected result over successive frames. The example value visually shows the final result when multi-domain detection and interplane processing are performed simultaneously. While detecting more objects, we can see that incidental false positives are not detected. Before showing the experimental result, I would like to describe experimental environment. The baseline of the object detector is YOLO-V3 with adaptively special feature fusion. We used the pre-trained weight with the MS-COCO dataset. And for training of AlbedoNet, we use also the MS-COCO dataset too. For validation, the ACRV validation dataset was used. The metric for comparison is the PDQ score. The definition of the PDQ score can be found in the lower right corner. This is a table showing quantitative result of multi-domain detection and interplane processing using Albedo images. We can see that many objects are additionally detected because of detection in the multi-domain. The unnecessary false positives were removed through interplane processing to further improve the PDQ score. This experiment compares soft-DropBlock with existing method. Low gamma means it preserves true positives well and effectively eliminates the false positives. As a result, we can find that the soft-DropBlock with high standard deviation removes information meaningfully and provides more samples than dropout. This table below shows how effective stacked NMS is in multiple inferences. Stacked NMS improves the PDQ score by suppressing a great number of uncertainty underestimated results than conventional NMS. In addition, we observed that soft-DropBlock exerts positive synergy with stacked NMS through the PDQ score. The following table compares the performance of each applied technique. We can see how much the PDQ score improves whenever each technique is applied. As a result, EPrOD improved the PDQ score by 4.6 points compared to the baseline. This means that EPrOD have obtained many results with better quality than baseline. In conclusion, we proposed EPrOD that applies 4 techniques to the MC-based EPrOD. The performance was verified in terms of the PDQ score. However, EPrOD still requires a lot of computation time because it still has to make several inferences. So we think future optimization studies are expected. Thank you for your attention.